Hello everybody, how are you? Before I get going here, what I'd like you to do is number 37 on page 242. You don't even need your book because I just wrote the question out here. Given this function f of x over the specified domain of negative pi to pi, this is a very just straight up basic question. I just want to start this screencast out with us just kind of making sure we really know what we're doing here, okay? What I'd like you to do is find the intervals over which this function is increasing, the intervals over which the function is decreasing, the intervals over which the function is concave up, where it's concave down, and then the x-coordinates of any points of inflection. Okay, so we're doing a full curve analysis. Feel free to work with me here if you'd like to, or you can work on your own and then stop. But what I started doing here, work on your own, then check. So here what I did was I found f prime. F prime, notice the chain rule, be careful. I asked the question, any first derivative critical points? And make sure I don't forget to take a look and say, are there any points where f prime does not exist? There are not. What about when f prime equals 0? Well, if f prime equals 0, I'm going to set each of these factors equal to 0. So I'm going to say over here, it's like, when would sine x plus cos x equal 0? Or, frankly, when would cos x minus sine x equal 0? And the reason why I plucked this question out is because I really want to make us work on some old stuff. Well, let's see. This is the same thing as saying, where will sine x equal the opposite of cos x? And I already know x is going to be some multiple of 45 degrees, or pi over 4, okay? And in quadrant 1 and in quadrant 3, okay, you hear that? In quadrant 1 and in quadrant 3, sine and cos have the same sign. In quadrant 2 and in quadrant 4, however, sine and cosine have opposite signs. So what angle, with a reference angle of pi over 4, okay, will terminate in quadrant 2 or in quadrant 4? Well, let's see. That would be, quadrant 2 would be 3 pi over 4, and then quadrant 4 would be 7 pi over 4. And here's where I'm not going to be careless. The domain is between negative pi and positive pi. That means I have to work between negative 180 and positive 180, which means that all the angles I name here have to be named between negative 180 and positive 180. The way I named this, 7 pi over 4, is not appropriate. 7 pi over 4 is past pi. But I could call this angle not 7 pi over 4. I'll just call it negative pi over 4. There I go. Two angles right here. Stated correctly within this domain where sine and cos have opposite signs. All right, let's go over here. This is saying, where will cos x minus sine x equal 0, or where does cos x equal sine x? Well, in quadrants 1 and in quadrant 3, right? In quadrant 1 and in quadrant 3, we have cosine and sine, right, having the same values. So now when I look back here, I have 1, 2, 3, 4 first derivative critical points. Do you understand, everyone? 4 first derivative critical points. I'm going to go over here and do a first derivative sign analysis. And I'm going to make sure I'm really thorough. I'm only doing a sign analysis, again, over the interval in question. So I only care about f prime between negative pi and pi, okay? I'm just going to make that number line. Because this number line is not for all real numbers, I want to make sure I don't test numbers beyond those points. All right, let's go ahead here and put in my my values that I know. This is negative 3 pi over 4. This is negative pi over 4. This is pi over 4. And this is 3 pi over 4. And at all these critical points, f prime equals 0, right? But the question is, what is the sign of f prime in the intervals between those critical points. What is it? I just realized these look like negatives, but they're not. So what we're going to do, everyone, is pick convenient values of x, say between negative 3 pi over 4 and negative pi, between negative pi over 4 and negative 3 pi over 4. And people always ask the question, in this interval here, can I pick x equals negative pi? The answer is, yes, you can. So I'm going to pick negative pi for this interval. You know what convenient angle lands right between these two? Oh, I love it. Negative pi over 2. Okay? 0 lands right in here. Pi over 2 lands here, and pi right here. Now, I have to test the sign, right? Where's f prime? Where's f prime? Here's f prime. Here's f prime. Here it is, f prime. All right, I'm going to let you go ahead and test in the values and see what sign you get for f prime up here. I wonder if any of you did this. Here is the sign, but you know what I did? See, we're always very savvy, everyone. When I was thinking of plugging in these values, right, of x, I mean, it's doable here. It's a little bit clumsy, but I noticed something. See how this is just cos x plus sine x times cos x minus sine x? That's the same thing as cos squared x minus sine squared x. That version of f prime, oh my goodness, does that make my life easier than just plugging and chugging, right? You want to start doing that, boys and girls. You want to start asking yourself, if you ever find yourself down in a pit of despair, and the pit of despair is where you're saying to yourself, seriously, I have to plug in these values of x and then kind of keep track of what's positive, negative, and positive, negative. 9 times out of 10, if you find yourself in that mindless, simple math pit of despair, there's some way out of it. And this is what I just saw here. When I have f prime written this way, testing these points, while still tedious, it just makes it a little bit easier. All right, I'm going to have you write out the intervals of increase and decrease because we had some issues with that in the quiz. I'm going to go over here and say f, oops, let me use a different color. F is increasing on, intervals of increase and decrease are always inclusive on the interval of x from. Okay, the intervals of increase and decrease are always inclusive unless f prime doesn't exist at an endpoint, right? Or f doesn't exist at an endpoint, but otherwise it's inclusive. All right, here we go. Negative pi to negative 3 pi over 4, inclusive. Negative pi over 4 to pi over 4, inclusive. And 3 pi over 4 to pi, inclusive. Okay? F is decreasing on the interval of x from negative 3 pi over 4 to negative pi over 4, inclusive. And pi over 4 to 3 pi over 4, inclusive. All right, intervals of concavity, and this is kind of going to kind of reinforce my point again. If we're looking at intervals of concavity, okay, intervals of concavity, that means I have to take the second derivative. Oh my goodness! If I take the second derivative, and if I look at f prime, I want to pick the easiest version of f prime that I possibly can. Okay, the easiest version of f prime. And if I look at f prime above, right, I'm telling myself I'm actually really happy that I rewrote f prime this way, because I don't want to deal with the product rule with this. I mean, I can do it, certainly, but why dive into a mess? We don't need to. I'm going to use this version of f prime. Okay, so now f double prime, I'll go over here. Look how neat my work is. You know, not that I'm being impressed with myself here, but look how concise and neat. You know, I'm not making any, you know, my pencil's not vomiting all over my paper. F double prime. Okay, F double prime is going to equal, okay, 2 times, well, 2 is just a constant, okay? F double prime is going to be, let me write this down, the derivative with respect to x of 2 times cos squared x minus sine squared x. Albert, this is for you. If you're taking the derivative with respect to x of any constant times a function, this is the same thing as just saying 2 times the derivative with respect to x of cosine of square root of x minus sine square root of x. In other words, any constant factor you can just pull straight through, and it'll just kind of wait until you take the derivative here. All right, the derivative with respect to x of cos squared x, don't forget, cos squared x is the same thing as cos of x squared. So we've got some chain rule going on. This is going to equal 2 times, all right, I'm going to deal with this, 2 cos x times negative sine x, minus 2 sine x times cos x, and this at the end of the day is going to equal 2 times, this is negative 2 cos x sine x minus 2 cos x sine x, negative 4 sine x cos x. If I really want to just make my life easy, which I do, negative 8 sine x cos x. Okay, this is f double prime. That's f double prime of x right here. Now, finding second derivative critical points. There are no points where the second derivative doesn't exist, but where are the points where the second derivative equals 0? Okay, where will sine x equal 0? Where will cos x equal 0? Oh, don't forget, it's only between negative pi and pi. So I'm going to go down here and say, sine x will equal 0 at x equals 0 and x equals pi. Cos x equals 0 at x equals pi over 2. I want to say 3 pi over 2, but 3 pi over 2 is beyond our specified domain. So pi over 2 and negative pi over 2. Okay? And I'm going to walk over here and do a nice second derivative number line. And I'm going to remind myself, look how slow. I'm just going methodically, right? Making my way. I want to remind myself I only care about the interval from negative pi to pi. Let's see, I've got negative pi over 2, 0, pi over 2, oh, and pi, oh, and also negative pi, interesting. Because, I didn't write it down here, but negative pi 2. And so f double is 0, all of these, all right? Go ahead and do the sign analysis then, if you would, please. Okay, here's my sign anal. And then, just like before, I'm going to write f concave up on intervals of concavity, open, 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 open. Negative pi to negative pi over 2. Whoops, I just gave the intervals of concave down. CM. You know what? I'm just going to change this word to concave down. And 0 to pi over 2. Concave up on interval of x from negative pi over 2 to 0. And pi over 2 to pi. X coordinates of points of inflection. Points of inflection, by definition, are points where the second derivative changes sign. Everyone in the know, everyone at the cool party knows that POI stands for points of inflection. At x equals negative pi over 2, at x equals 0, and x equals pi over 2. Okay? Again, just kind of a walk through old stuff. A little bit long and arduous, but a nice, just kind of solid review where we make ourselves go through the algebra. And this may have taken a while, and yes, it did, but you know what? It's good. It's good for us. All right. Now, what I want you to do, if you would, is go with me and look at page 243 and look at number 63. These questions are among my favorite. I love it. Page 243, number 63. Go there, please, okay? And I want to read the question with you. And so pause me if you have to go run around, your house and find your book. When you come back after you run around, just replay me. It says that in 63 you have a tank right? That tank is that kind of bulbous shape. The tank in this case looks kind of like this, right? Kind of bulges out in the middle, all right? And it says that this tank is being filled with water at a constant rate. Make a rough sketch of the graph of the water level versus the time. And so here we're going to make a sketch of this, the water level as a function of time. Now, assuming water is pumped into this tank at a constant rate. Now, the water level as a function of time, we know whatever graph we sketched here, it's going to always be increasing. Obviously, always increasing, because if water is pumped into here, assuming there's no hole, which there's not, right, the water level will always be increasing. But given the shape of this glass, right, how is it increasing? In other words, would the height be increasing more rapidly here and less rapidly here because the vase is wider, and then would it kind of start increasing more rapidly here? What do you think? Go ahead and give it some thought, and then, come back and replay me. Well, it turns out, somewhere in the middle, the height of the water, the height is increasing at its slowest rate. Isn't that interesting? The height is increasing at its slowest, which means that the height is going to be increasing, right? We know this function is always increasing. But y, right, the water level, should be increasing at its slowest rate somewhere in the middle. What that means, everyone, is that the slope of the line tangent to the water level function should be least positive somewhere in the middle. So here's what I'd be comfortable accepting, like something like this maybe. Right? If you look at if this is the water level, if we think about this, right, water level is, if you look at the slope of the line tangent, right, the water level is such that it's increasing right here. How it's increasing decreasingly. Because at this point where it's increasing decreasingly, that corresponds to this part of the curve, right? Because as the vase widens out, certainly the rate at which the height of the water increasing is going to slow down. But then it starts to increase increasingly, and that corresponds to the fill for this part of the vase. Isn't that interesting? So there is a point of inflection right here, right? A point of inflection is where a curve goes from bowl down to bowl up when the concavity changes, right? All right, so in that spirit, let's do 64 together. 64, so fun. These are so fun. 64, all right, 64. And the shape of this, it looks like, I'm going to exaggerate it. The shape of this vase is like this. It kind of like bowls in, right? But until this, where it kind of funnels in, right? It's kind of like a straight cylinder at this point, right? Straight. And this, okay? So here, what would this look like? Well, for this part of the function here, how would the height of water be increasing? H should be increasing at what rate? H should be increasing at a constant rate. So H should be looking something like that, right? That part, some linear, as long as it's linear, right? That corresponds to like this part of it. Uh-oh, but then what happens in this part of the vase? It's still increasing. Is it increasing decreasingly or increasing increasingly? Yes, it starts to increase decreasingly. So I'm actually going to modify this a little bit. So linear. Then it keeps increasing, but it increases decreasingly. So linear, something like that. I'd accept that even, right? Isn't that great? It's so great. It's like E. Okay? So what I'd like you to do for homework, please, would you please go ahead to page 243, take care of numbers 65, numbers 66, number 68. 68 I like quite a bit, number 68. And then also, would you please look at also Oh, let's see. Page 253, number 43. And that is it. How about that? Goodbye.